performance today, big portion of flight mechanics. So if I say flight mechanics, it's kind of a subject for you, which covers around 18 to 20 marks in your exam, but it is broadly divided into two portions. One is performance and the other one is stability. Now, again, these are subdivided into many topics. So I'll be focusing more on performance part today. And then once this performance part is done in the coming classes, we'll move on to the stability part. And then we'll see the syllabus for stability, like static stability and dynamic. Then which is further divided into longitudinal, lateral, and directional stabilities. All right. So I'll be discussing about performance part today, what the syllabus is, and then mostly the first 2 points. So let's go step by step and discuss about this. So if we have performance, all right. So to be very precise, your performance is divided into two portions again. One is unaccelerated performance, all right, and another one is accelerated performance. Now, what do you mean by this? You will get these terms once we talk about small bits and pieces about this. So let's take an example. Let's say you have an aircraft, all right. The first thing we do in aircraft is we have a takeoff, correct? Your aircraft moves on ground, have a lift-off velocity, and then goes up in the altitude. So the first portion, what your aircraft do, or the first maneuver which your aircraft do, is referred to as the takeoff. I'll name everything slowly. Then after this, you do a cruise climb. To be very precise, it is kind of a linear line. You don't have any loop here. That we need to discuss a lot. What do you mean by cruise climb? What do you mean by steady climb? All these conditions. Then once you have reached your altitude, typically 11-kilometer altitude, we will cruise for certain distance wherever we want to go. So the maximum part of the aircraft is spent during this cruising time. Once you reach your destination, which is closer to the place, you start your descent. All right, so you directly come down like this. Then you do maybe a loitering. That we'll discuss. What do you mean by loitering? All different colors I will discuss in detail. And then you initiate your landing, and then you stop your aircraft when you have reached your destination. All right, something like this we'll observe. So if you clearly and slowly observe each of these phenomena, right, we have takeoff. Guys, please listen to this. Because you should first know what you are going to study throughout your performance part and why these are divided into different topics. So you have takeoff and you have landing, and these two parts are the part at which your velocity is changing. Now, what do you mean by velocity is changing? Here, your velocity is increasing from 0 till some takeoff velocity. Let's say takeoff ends here. And here, let's say your landing initiates from this point and it goes to 0 velocity. So in takeoff and landing, both your velocity is changing. In one, it is increasing, and the other one, it is decreasing. When your velocity change, from our basic formulas, we know velocity change is basically known as acceleration. So whenever we have change in velocity in any maneuver, we'll say it comes under accelerated flight performance. And whenever your velocity is constant, if this term is constant derivative will be 0. And if your acceleration is 0, in other words, we are saying velocity is constant, comes under unaccelerated flight performance. So you have two broad topics, accelerated performance and unaccelerated performance of aircraft. All right. Now takeoff and landing, it's perfectly fine. Then we come to this climbing part. Now this climbing part, I feel people have this doubt, but this climbing part is a constant velocity maneuver. You never increase your velocity here. That's what is referred to as cruise climb. All right, so when we enter into climbing, we'll talk about more in detail. Then you have cruise, at which this is most of the time is referred to as trimmed flight or steady state and level flight. So this is also a maneuver in which your velocity is constant. Then you have a descent. That means you are having at some altitude without any thrust production, you come down. Here also you will try to keep your velocity as constant. So if you see this precisely, right, forget about first 2 points. Don't worry about this because this whole lecture is dependent upon first 2 points only. But if you see this clearly, gliding flight is this portion. Climbing flight is this portion. When we say range and endurance, absolute and service ceiling, all these are related to our steady state and level flight. So to be very precise, these three regimes we will talk about in unaccelerated flight performance, where velocity will not going to change. How velocity will not change? So your equations will be following that particular part. You should not violate these conditions when you're developing the equations. But when we come to takeoff, when we come to landing, and maybe you have heard about the term turning flight. Turning flight is usually incorporated here. You need to go to certain distances, right? Certain location. So turning also come here. Then during takeoff itself, you have a pull up maneuver and you have a pull up maneuver in your flare as well in landing. So we have small topics like pull up maneuver, pull down maneuver, takeoff, landing, turning, pull up, pull down. All these comes under accelerated flight performance, which is our second part. And first part is unaccelerated performance, majorly focusing on steady state and level flight, climbing and gliding. All right. And when we say performance, we'll be asking all the questions. What is the maximum altitude you can go? What is your velocity here? What should be your CLCD at these conditions? If you want to maximize range of an aircraft, if you want to maximize endurance of an aircraft, at what velocity you should fly, what should be your CL values, and so on. So many different link question will come from this. So performance part will be clearly answering what all flight conditions are needed to operate at these particular altitudes. Now, this is just an overview of what we're going to see in the coming lectures. I'll straight away start with this part, unaccelerated flight performance, this part in which we will discuss morely about steady state and level flight first, and then slowly build our equations for gliding and climbing as well. All right. So I'll straight away go to the topic. So now what we are talking about, we'll say steady state and level flight. And guys, please feel free to ask your doubts if you have any. All right. So when we say broadly steady state and level flight, you people must have seen these equations before. If you have an aircraft which is flying at some altitude, now the conditions or the forces which are acting, your engine is producing thrust in the forward direction. This is the reason you are moving forward. All right. You're also, because of this, because you're moving in air, you have a drag component which is coming up. You always know that weight acts downwards. All right. And you have lift which is balancing out the weight. So I'll try to go each and every term, and then we'll decide different depending upon different drag, minimum power, minimum D by V condition. All these conditions are why defined. Why we are talking about these conditions when we come to performance, the equations, and then few numericals on this. All right. Now I'm coming to that. So when we say steady state and level flight, level means your altitude should not change during this flight design. Now, what do you mean by altitude should not change? You should not go up. You should not come down. That means you should have lift exactly balancing out your weight. Please don't worry about this 12.75. It's a typo. So you have first equation that your lift should be balanced by weight if you are in level flight. Level flight means you should not change the altitude. First condition. Second condition is steady state. Now, what do you mean by steady term? Steady term in fluid, aerodynamics, or in maths, anytime, whenever you say steady, anything should not be changing with respect to time. Now, what do you mean by this? If anything doesn't changes with respect to time, that means your velocity cannot change with respect to time. What do you mean by this? Acceleration is constant, and this is unaccelerated flight condition, constant velocity. So this is constant velocity, meaning of this steady state term. Now we need to look into this more part. What do you mean by constant velocity? When you move at constant velocity, try to keep this in mind. We will be talking about thrust is equals to drag term. So this will not increase so that this will not balance it. Or in other words, your aircraft will only and only produce that much thrust to overcome drag. Your engine will not operate at, your engine can produce more thrust, because in turning flight, you have to produce more thrust. If anything is deployed, you have to produce more thrust. So thrust is equals to drag means you are not going to change your velocity anytime. You're flying at constant velocity now. You're flying at constant velocity. That means we're talking about steady state. And when we talk about level flight, means we're not going to change the altitude. All right. And these two are clubbed together. Now, how they are clubbed together. So I guess most of you, I will go into this equation in detail because this is what we need to understand better. I hope and I assume that you people have seen this formula. Lift is equals to half rho v square s into CL. So whole lecture is dependent upon this formula today. All right. So just think about this. If during this steady state and level flight, your velocity changes, if you're going to change this, all right, this part, increase or decrease, your lift will change. If your lift will change, that means you will no longer balance your weight. If your lift is more than weight, you will gain altitude. This is bad. We don't want this. If your lift is less than weight, you will lose altitude. This is bad. We don't want this. And so we should be in a position to maintain constant velocity. But sometimes there are regimes in which pilot has no other option. He or she has to change the velocity to meet the flight conditions. But we don't want to violate this equation. So there is an option for pilot to control the CL as well. In the end, I want same lift. So I'll come to that part. What do you mean by changing CL and keeping velocity constant? But steady state and level flight means your lift should be equals to weight. Your thrust should be equals to drag. And we have these two equations valid for steady state and level flight throughout your performance syllabus when we talk about this condition. I will show you all the numericals step by step. We'll do it slowly and then we'll move ahead. All right. Any doubt, feel free to ask. I will discuss this. Otherwise, I'll keep in mind like your understanding and I can move forward. Now, let's talk about why we are doing all this. All right. So you said that lift should be equals to weight of the aircraft. Correct? And you have an aircraft whose weight, I'm just giving an example now, let's say is 1000 Newton. Guys, please listen this part. This is an important theory. So no matter what, if I want to maintain one steady state and level flight, my lift should be equals to, these are cruise conditions. Your lift should be equals to the weight of the aircraft if you want to maintain same altitude. All right. I have already seen that lift is equals to half rho v square s into CL. All right. Now let's zoom in into this formula. Rho is the density at the altitude at which you are flying. So I'll be talking about true airspeed, equivalent airspeed, all these topics in a bit. Velocity is with which your aircraft is flying. S is the wing planform area. This is an important aspect to understand. When we say planform area, it is something like this. Let's say you have an aircraft, all right, which is having wing something like this. And let's say it's swept back. All right, something like this you have your aircraft wing. Now, when we say planform area, when you see it from top, you're going to see a rectangle kind of thing. That's what you observe, right? So some span, some chord, if it is not tapered, and I'm assuming very simple wing. So this is the area which you see as the planform area. Planform area is the area, if you light bulb over it, what shadow you will going to get in below is nothing but your planform area. Now there are different areas like wetted area that we'll talk about, cross-sectional area. There are different areas which will come in different equations. But whatever area S you will see here is the planform area. So whatever you see from top, you don't worry about the slopey thing because this is, you are using your NA foil here, right? So don't see that we need to capture this curve to calculate the area. No, anything from top, that area should be considered here. All right, this is just a basic. You should know this thing. I have created few questions in your test series regarding the area, which area to consider. Don't worry about this, please. Now understand what I'm trying to get into at this point. The only thing pilot need to maintain is this 1000 Newton. All right. Now there are multiple options. If you need, and I need your response in this, if you need 1000, let's say your density is constant, you're flying at the same altitude, you're not going up and you're not coming down. Now what I'm doing is, let's say I have velocity of 100 meter per second square and the corresponding CL value. I'm just giving an example. Let's say 1.5. If you substitute these S value and rho value, you will get this as 1000. But can I say, just say true or false or yes or no, it is possible for me to get this 1000 if I fly at, let's say, 110. But for that, I should reduce this value. Or there is a possibility that I fly at 1000, but what I'll do is I'll fly at lower speeds. But I need to increase this value then. But in all these cases, I am getting 1000, 1000, 1000, and this is perfect. That's what my intent is, right? Guys, this point makes sense. Is this fine? All right. So the question is, at what velocity your pilot should fly? Is he or she should fly at 100? Is he or she should fly at 110 or at 90? And there are multiple options, 91, 92, maybe 200. Depending upon that, you need to update your CL values as well. Now, you people know your CL. You should know this. If not, I'm covering that part now. Your CL can be controlled by your angle of attack because you're using a particular kind of airfoil in your wing. So pilot can control this. Pilot can control the velocity as well with the help of your engines. You can have more velocity, you can have less velocity, but in the end, I don't want 1000. All right. Now the question comes, it's perfectly fine. We do this. If you see this topic precisely, right? This one, range and endurance or gliding, climbing. The question comes, what is the best velocity with which we should fly so that we can maximize range, so that we can maximize endurance? Now, I'm not going into range and endurance for in detailed part as of now, because my intent is slightly different. First, we need to first develop the equations for this steady state and level flight. But the intent is simple, guys. If you want to maximize anything, should I fly at any of these conditions or there is one best possibility? No, 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 Siddharth, no, no, not at CL max. I'll come to CL max in a bit. So Siddharth tell me CL max. Ankan told me minimum drag. Now the question comes: should we really operate at condition in which you have minimum drag, or you should operate in a condition in which your engine is operating under minimum power, or there is one more condition which is referred to as minimum D by V condition? All these conditions corresponds to same lift all the time. But what is changing for all these three conditions? Your velocity and your CL will be different in all the cases. Now the question is, during climbing, should I fly here, here, or here? During cruise, should I fly here, here, or here? Or there is a failure of my engine, I want to protect my people, in what condition I should fly so that I can go to the maximum distance? Definitely it depends upon the engine, but it depends upon the equations we're going to develop from now on as well. So first point which I want you to understand is this point clear to you, what we are trying to identify and find out? We try to find out from in today's lecture, we'll do all these equations, that at what condition we should fly, and at what condition means what should be our velocity and what should be a corresponding CL, so that we can maintain this condition. This is the reason, if you see in your syllabus, minimum drag, minimum power, and minimum D by V condition comes into picture. So before actually starting my equations, do you understand what we are looking into and what our final motive is in this particular unit? Tell me, guys. Okay. Okay, fine. So let's move ahead. All right, and define few conditions now. The first condition which we want to define is what is you must have known on this, but I'm trying to cover from the basics, so I don't want to rush into this, which is referred to as stalling speed. We sometimes refer to it as V stall. All right, and then we see the condition what this corresponds to. All right. Now, if you recall your aerodynamics, or if you don't know this, it's perfectly fine. If you have an airfoil, which is operating at certain angle of attack, at that angle of attack, that airfoil will have certain value of CL. All right. So for symmetric airfoil, the graph looks something like this. For unsymmetrical airfoil, the graph will be shifted towards left-hand side. So my intent is not aerodynamics. I'm not going into that part. But what we are trying to show here is if you have zero angle of attack, zero CL, if you increase your angle of attack to 2, 4, 8, maybe 12, and so on, and your corresponding CL value is increasing. That's what the meaning of lift curve slope is. But if you see it very precisely, there is a point after which your CL decreases drastically. If you see after this point, your CL decreases, and this is referred to as the stalling point. So you have alpha stall here. And corresponding to this, you have the maximum value of CL max. After this, you cannot increase your alpha values. If you increase it, there will be flow separation. You will not going to produce lift, and your lift will decrease drastically. So throughout your performance, we will always be in this linear zone, straight line. We will never cross this part. We will not talk about anything about flow separation or stalling problems in performance. We will always keep ourselves in the good part. We will not violate this. The stalling phenomena, flow separation problems will be part of your fluid mechanics part. All right. Now, that means there is a point at which you have maximum CL max, and the corresponding you have alpha stall. Now, if you see this precisely, keep this in mind still. Your lift should be equals to weight of the aircraft, which can be broken down into half rho V square S into CL. So, if you operate at CL max, you cannot have CL max greater than this. That means you have the minimum velocity possible, which is referred to as V stall. So guys, V stall is the minimum speed at which your aircraft can fly without losing control. You can never go below V stall. It is not possible. The reason, if you go below V stall, you are not going to maintain this steady state and level flight. You will lose altitude because your CL max has reached its maximum limit. If this is maximum, this is the least velocity with which I can fly. So V stall, if I'll see from the formula, if you cross multiply this, it is nothing but 2 into W divided by rho S CL max under root. Very, very basic formula. You 100% have seen this a lot before. But is it fine for you people? Now, why we say that V stall is the minimum speed with which your aircraft can fly. Now, we'll talk about this in detail that you sometimes cannot even reach V stall. Before that, only the failure happens. But that is different depending upon the engines. First of all, the intent is, do you understand what do you mean by V stall, guys? So the CL max, keep this in mind, is your airfoil property. If you have different airfoil, you have different CL max and you can fly at different velocities itself. So I hope I have answered your question, Shashank, that what is CL max or what is V stall or something. Is this fine, guys? Yeah, it's the threshold velocity. It's the least velocity with which you can fly. All right, perfect. Now let's define few small terms, and then I enter into my major concern of 3 different conditions. And you know the intent, why we are doing this. So there is one term which most of the time in many numericals they're going to give you. They will name this term weight of the aircraft divided by the wing area as one term which is referred to as wing loading. It is usually denoted by small w. And if you see formula wise, it is nothing but weight of the aircraft divided by the planform area. If you see the units closely, it's no significance, guys. Just they have clubbed this into one term. Rather than writing w by s, they will write small w. Be very cautious in your exams when you're doing this, because you need to understand the units. You know, weight is in Newton and your area is in meters square. So unit of wing loading will be Newton per meter square. That's what should be used all the time. So maybe you can also see this. You can also write Vstall or any velocity as 2 small w divided by rho CL max under root. This is just one condition or one quick formula if you want to understand. Is this fine? Is it clear? Perfect. So let's move ahead and understand the equations in a slightly better way. Now I'm coming to the major part, guys. It will affect every velocity, not only Vstall. This is just an example. You can have simple velocity here if you use corresponding CL. So whatever CL you substitute, that corresponding velocity you will get, because other part are constant, right? So if you substitute maximum CL, the corresponding velocity is the minimum speed. I mean, it's clear, right? You want same number here. I just gave you an example. Let's say you want 1000 Newton here. So there are two ways. You can either change velocity or you can change CL max or CL. If this is maximum, this can go to least, right? Multiplication should give you 1000. All right. Now let's understand or develop our equations more in a slightly better way. Now comes the major equation, which we need to understand properly, which is referred to as drag polar equation. All right. And you must have seen, let me define this equation with the naming properly, and then we need to update and play with this term. So when we say drag polar, it basically gives you the drag coefficient. And how this drag coefficient is needed? You know, drag is also half rho v square s into CD. So if you want minimum drag, it's better to have minimum CD. That's the intent. But is it always minimum CD good for us, or there are other conditions as well? So that's the question we want to answer. Now, if you zoom in into this drag polar, right, this drag polar consists of two parts. One is your profile drag, or to be very precise, people say this as zero lift drag coefficient. I'll explain this term. And the other one is referred to as induced drag. So I don't expect you that you know both these terms, which is perfectly fine. But now we're going to go and understand this part. So this is referred to as zero lift drag coefficient. This is also referred to as profile drag. Now I hope the name will give you some idea. This is also known as parasite drag coefficient. These are the different names given to it. It is simply and simply dependent upon how big your body is. You people know, if you have an aircraft like this and if you have an aircraft like this will have less drag compared to this. This is all captured under CD naught, which is referred to as profile drag or parasite drag or zero lift drag coefficient. All right. But if you come to the next part, second part of it, this is referred to as induced drag coefficient. So I'm not expecting you that you people know this,